Welcome to this pre-class video on amines. Well, amines are an important class of organic compounds, and you can have three different classifications. And the classification of an amine depends upon its number of bonds between a nitrogen atom and carbon. So let's do an example. If you have a primary amine, then you're going to have a nitrogen, and you're going to have one bond to carbon. And I'm not going to specify what that carbon is bonded to because it doesn't matter now. So you have one nitrogen-carbon bond, and therefore you have two bonds to hydrogen and a lone pair. But the classification of an amine can be determined by looking at the number of bonds between nitrogen and carbon. One nitrogen-carbon bond, a primary amine. Well, maybe you'll see a pattern here, because in a secondary amine, there are two bonds between nitrogen and carbon, and therefore only one bond to hydrogen, and then a lone pair. Well, how about a tertiary amine? Well, you've got three bonds between nitrogen and carbon, and you've got a lone pair. So here are some examples of the three different types of amines. So, three different types of amines. One exception to what I've told you is if you have a nitrogen and you have a carbon attached to that nitrogen, but that carbon is what we call a carbonyl group, a C double bond O, then this is not an amine. It is what we call an amide, A-M-I-D-E. And amides have very distinct properties from amines. So that being a C double bond O makes this a very different type of molecule. But you can still use these rules to determine a primary, secondary, and tertiary. But if you see a nitrogen directly attached to this carbonyl, then you know you do not have an amine, you have an amide or amide. Well, we're not going to name amines, which is good news, I guess. But one of the things we're going to talk about are properties of amines. So that's going to be a trend here with organic compounds. Let's talk about boiling point and water solubility. Well, I've given you two amines here, A and B. They're both primary amines. So what I need for us to do is to predict which one is more water soluble and which one has a higher boiling point. Well, we've got some rules for that, and I've given you a handout that gives you the rules for helping you work through properties. Let's kind of go through that, or through this analysis fairly quickly, because hopefully you're getting used to doing this over and over again. Well, with water solubility, we know that the ability of a molecule or an organic compound to be soluble in water depends upon its ability to form hydrogen bonds with water. If you're a molecule and you want to be soluble in water, you better form as many hydrogen bonds with water as you can. So, in terms of A and B, both A and B have a hydrogen bond capacity, which we have defined as a number of donors plus the number of acceptors. Both of these have a D plus A of 3 because the number of donors is 2, the number of acceptors in each one is 1, so that's going to be 3. Don't forget about the lone pair on nitrogen in these two amines. So, can hydrogen bonding explain the difference in water solubility of molecule A and B? No, because it's a tie. So, you now have to turn to the R group. Remember, this is what we would call R. This is what we would call R. And, hey, one R group is larger than the other, which makes the R group of B is larger, but it's more nonpolar. So basically, molecule B, I'm not saying it's nonpolar, it's more nonpolar than A, though. We know that. because it has a larger R group. It's got more of hydrocarbons, and hydrocarbons are nonpolar groups. And since B is more nonpolar than A, or B has a higher nonpolar area, as your handout probably describes, then we know that A is more water soluble than B, because it is more polar, because B is more nonpolar than A. Again, the more polar a molecule, the more water soluble it tends to be. Alright, now what about boiling point? Well, boiling point, again, depends upon the ability of individual molecules to hydrogen bond with themselves. So, both A and B can H bond with itself. So if you have two molecules of A, can they form a hydrogen bond? Yes. If you had two molecules of B, can they form a hydrogen bond? Yes, because they both have at least one donor and one acceptor. So, in terms of boiling point, being able to hydrogen bond with yourself raises the boiling point. And so, both of these can do that to a similar extent. So, this is a tie again. But we also know that size of a molecule can influence boiling point. The larger the molecule, the more dispersion forces it can form with itself, the higher the boiling point typically. So B is larger than A, and as a result, since hydrogen bonding is a tie, the size is going to play the major role. So B is larger than A, so B has increased boiling point. Again, we're going to do this a lot. Properties associated with organic compounds, and we've just kind of, to prepare for class, looking at two different amines and making predictions. Well, another important aspect of amines that's going to be a major role in class is amines are bases. That is, they accept hydrogen ions, and usually this happens in water. We do most of our things in water in this class. So, a base accepts a hydrogen ion, or bases are hydrogen ion acceptors. So that means if you start out with an amine, let's just draw some generic primary amine. It could be a secondary amine, it could be a tertiary amine, it doesn't really matter. And we add a hydrogen ion. Again, this is probably happening in water. We're not going to show the water in this case, it doesn't really matter. But an amine can react with a hydrogen ion, and hopefully you can predict what I'm about to draw. You've got RNH2 plus H plus. Well, add them together. RNH3 positive. RNH3 positive. And this should make sense to you, because you know, based upon a discussion of formal charge, and this is in your playbook, if you have a nitrogen with 4 bonds and no lone pairs, that is legal, that is legitimate, but the nitrogen will have a formal charge of +1. So this basically is what we have here. But you knew it had a positive charge anyway, because if you have something with no charge plus something with a positive charge, and you get one product, that product has to be positively charged. So we know this is the base form of the amine, but in water you can also have the acid form, and they are in equilibrium. How are we going to determine which is the major form or the predominant form in water? Well, every weak acid has what we call a pKa, and we've talked about pKa previously. pKa is a numerical, measure of the acidity of a particular organic compound. That is a weak acid. And the lower the pKa, the more acidic the molecule is. The higher the pKa, the less acidic it is. But let's just say the pKa for this amine here is 10. And I'm drawing it over here on the acid side because pKa is the acid dissociation constant. So it's associated with an acid. Now, how do you know if this molecule is in water at a given pH, whether you're going to have the acid form as the major form or the base form? Now, that's an important question because one of these forms is positively charged, the other one is not charged at all. So this is an important question in which to tackle. So let's just say we're at pH 7. So you adjust the pH of the water solution to 7. Then which is the major form? Well, we have some rules, and we have gone over these rules before. If the pH of the solution is less than the pKa of the weak acid, the acid form of the molecule predominates. If pH of the solution is greater than the pKa of the acid, then you have the base form is greater than 50%, or the predominant form or the major form. If pH of the solution is exactly equal to the pKa of the molecule, then you have an equal contribution of acid plus base. So this would be 50%, and this would be 50%. Well, in this case, at pH 7, the major form of our molecule well, let's look at it. The pH is less than the pKa. So the major form is going to be the acid. That's it. So we're not getting into specifics about what is the percentage, but we know that you put the molecule, a general, just kind of general primary amine in water, adjust the pH to 7, the acid form will be in greater amounts, be greater than 50% in water. All right, hope this video was helpful.